There's a star so vast that if it replaced our Sun, Mercury, Venus, Earth, Mars, even Jupiter, its surface would stretch towards Saturn's orbit. You could pack 10 billion suns into its volume, and yet in cosmic terms it's fragile. So large it defies comprehension, yet so unstable it shouldn't even survive. How can something this immense exist without collapsing under its own gravity or ripping itself apart from within? If mysteries like this ignite your curiosity, subscribe and explore the universe with us. Start with the radius. 2,150 times larger than the Sunday. If the Sun were a basketball, Stephenson 2-18 would be a sphere 2 kilometers wide. You could walk around it for an hour and still not complete one lap if it were solid, which it isn't. But we'll get to that. The volume is where your brain starts to falter. 10 billion suns. Not stacked like bricks contained. Picture the sun, that massive furnace 93 million miles away, the thing that powers every living cell on Earth. Multiply it by 10 billion and cram all that space into one object. If you tried to count to 10 billion saying one number per second without stopping for sleep or food, it would take you 317 years. Despite that staggering volume, the mass is only 12 to 16 times the sun's. The density is absurdly low. If you could stand on the surface, and you can't because there's no surface, just gas thinning gradually into space, the atmosphere around you would be more rarefied than the best vacuum we've ever created in a lab on Earth. You'd be standing inside a star, and the air would be thinner than the air at the peak of Everest. Not by a little, by orders of magnitude. Light takes 9 hours to travel around the star's equator. Around the Sun, 14.5 seconds. Around Earth, 1/7 of a second, 9 hours. That's a full workday. You could start at sunrise, and by the time you clocked out at 5, light would have just completed one lap around Stephenson 2-18. If it were dropped into our solar system, not only would it consume the inner planets, but its outer layers would brush Saturn's orbital path, 1.4 billion kilometers from the center. Saturn orbits at roughly that distance. Neptune, the farthest planet, sits 4.5 billion kilometers out. This star wouldn't quite reach Neptune, but it would dominate nearly 1/3 of the solar system's span. The temperature at the surface is 3,200 Kelvin, about 3,000 degrees Celsius. Sounds hot, but the sun's surface is 5,800 Kelvin. Stephenson 2-18 is cooler. That's why it glows red instead of yellow. Red supergiants are cold, relatively speaking. Their cores, hundreds of millions of degrees. But their outer layers stretch so thin across such a vast volume can't hold heat the way smaller stars do. This star is a test case for what matter can do under extreme conditions. At the core, plasma is crushed to densities we can barely replicate in particle accelerators. Atoms are ionized, nuclei are smashing together, fusion is roaring through layers of hydrogen, helium, carbon, oxygen. But 1 billion kilometers away, in the outer envelope, the density drops so low that calling it gas feels generous. It's closer to the interstellar medium, the near void between stars, than to any atmosphere you'd recognize. This isn't just a bigger Sunday. It's a different category of object. The physics that govern its structure operate at the edge of what's stable. Radiation pressure from the core, the outward push of light itself, is fighting against gravity, trying to collapse everything inward. The star is balanced on a knife's edge. If it were any larger, radiation would win and blow the outer layers into space. If it were smaller, gravity would compress it into a denser, hotter state. Consider the paradox. The largest star we've ever found is also one of the least dense. Volume and mass don't scale the way we expect. Bigger doesn't always mean heavier. In fact, the more massive a star gets, the more violently it burns and the faster it destroys itself. Stephenson 2-18 is enormous because it's dying. Its core has spent most of its fuel, and in response, the outer layers have inflated like a balloon losing its structure. So we have a star that challenges every instinct about size and density. A sphere so large, it would dwarf our solar system, yet so diffuse you could pass through its outer layers and barely notice. a furnace so powerful it shines 440,000 times brighter than the sun, yet so cold on the surface that it glows a dull red. But where is it? And more importantly, why can't we see it? You'd think the largest star in the known universe would be blazing in our night sky, visible to anyone with a backyard telescope. But it's not. For decades, we didn't even know it existed. The reason has nothing to do with distance and everything to do with what's hiding it. Stephenson 2-18 sits 19,000 light-years away, buried deep in the constellation Scutum. That's not particularly far by galactic standards. The Milky Way is 100,000 light-years across. 19,000 is practically in our neighborhood. And yet, for most of human history, we had no idea it was there. The problem is dust. Cosmic dust. Not the kind you wipe off a shelf, microscopic grains of silicate, carbon, and metal scattered throughout the interstellar medium. Between us and Stephenson 2-18, there's a thick curtain of this material. It doesn't just dim the star's light. It absorbs it almost completely, especially in the visible spectrum. Visible light, the wavelengths your eyes detect, gets blocked. Red light penetrates a bit farther, but even that fades. By the time any visible photons reach Earth, they're so faint that the star is effectively invisible. You could point the Hubble Space Telescope at its coordinates, and in optical wavelengths, you'd see almost nothing. The dust exists because stars make it, not intentionally, but as a byproduct of their existence. In the cool outer atmospheres of red giants and supergiants, atoms have enough time to bond. Silicon binds with oxygen, forming silicate molecules. Carbon atoms link together, creating soot-like particles. These molecules grow grain by grain until they're large enough to block light. Each grain is microscopic, a tenth of a micrometer across, maybe smaller, roughly the wavelength of visible light. And that's why they're so effective at blocking it. When light hits a dust grain, it scatters. Blue light scatters more than red. Red light scatters more than infrared. The dust acts like a filter, removing shorter wavelengths and letting longer wavelengths pass through. The space between stars isn't empty. It's filled with this dust, along with gas, mostly hydrogen and helium, with traces of heavier elements. The density is incredibly low. In the best vacuum chambers on Earth, we can achieve a density of about 10 billion particles per cubic centimeter. In interstellar space, the density is closer to 1 particle per cubic centimeter. But over 19,000 light-years, even that sparse material adds up, and in certain regions the density is higher. Molecular clouds, star-forming regions, the spiral arms of the galaxy. Stephenson 2-18 sits near the Scutum Centaurus arm, one of the Milky Way's major spiral arms. The arm is dense with gas and dust. New stars are forming. Old stars are dying. The region is thick with material. This is why the star remained hidden for so long. Astronomers in the 19th and early 20th centuries catalogued millions of stars. They mapped the sky in extraordinary detail. But Stephenson 2-18 wasn't on any of those maps. Not because it wasn't there, because the dust blocked the view. But infrared light passes through dust the way radio waves pass through walls. And in 1990, astronomer Charles Bruce Stephenson was conducting an infrared survey of the Milky Way when he detected a cluster of anomalously bright sources in Scutum. He wasn't looking for the largest star in the universe. He was cataloging red supergiants, which are known to emit strongly in infrared. What he found was Stephenson 2, a cluster containing 26 red supergiants, nearly 20% of all the red supergiants known in the Milky Way at the time. Among them was Stephenson 2-18. At first, it was just another entry in the catalogue, a bright infrared source, likely a red supergiant given the spectral signature. But when astronomers began measuring its properties more carefully, its distance, its luminosity, its temperature, the numbers didn't make sense. The star was too bright, too luminous for its temperature. The only explanation was size. To emit that much energy at that low a temperature, the star had to be enormous. And when they calculated the radius, it came out to 2,150 solar radii, larger than UY Scuti, which had previously held the title of largest known star, larger than VY Canis Majoris, larger than anything else on record. but the uncertainty is significant. Measuring the size of a star, 19,000 light-years away, obscured by dust, is not straightforward. The distance itself carries a margin of error. If the star is closer than we think, it's smaller. If it's farther, it's even larger. Current estimates put the radius somewhere between 1,900 and 2,400 solar radii. The exact number shifts depending on the model, the data, the assumptions. Early estimates placed the cluster at 98,000 light-years away. That would have made it one of the most distant objects in the galaxy. But those estimates were based on assumptions about the amount of dust absorption. Refine the dust model and the distance changes. New measurements using different techniques, parallax spectroscopy, comparison with stellar evolution models, brought the distance down to around 19,000 light-years. Still far, but not nearly as far. And with the revised distance came a revised size. If the star is closer, it doesn't need to be as luminous to appear as bright as it does. And if it's less luminous, it doesn't need to be as large to have the temperature it has. The radius estimate dropped, but even with the lower estimate, Stephenson 2-18 remained one of the largest stars known. For a while, UY Scuti was considered larger. Then new measurements revised its distance, and its size estimate shrank. Stephenson 2-18 moved into the top spot. But the title could change again. Measuring stellar radii is an evolving science, and the uncertainties are real. What's certain is this. Stephenson 2-18 is one of a handful of objects pushing the absolute limits of stellar size. It exists in a narrow window where physics still permits a star to hold together, but only barely, and it's surrounded by an envelope of its own making material it has shed over millions of years, forming a shell of gas and dust that obscures it further. The cluster it belongs to Stephenson 2, also called RSGC2, is unusual. Red supergiants are rare. They represent a brief phase in the life of massive stars lasting only a few million years. To find 26 of them in one cluster suggests the cluster itself is young, cosmically speaking. All of these stars were born around the same time, and they're all approaching the end together. The cluster is embedded in a molecular cloud. The same cloud that gave birth to these stars is now obscuring them. The irony is striking. The environment that created these giants is the same environment that hides them from view. The dust that hides Stephenson 2-18 isn't just interstellar debris. Much of it comes from the star itself. Red supergiants are prolific dust factories. Their cool, extended atmospheres allow atoms to bond into molecules and molecules to condense into grains. Silicon, oxygen, carbon, they combine into microscopic crystals and soot particles that drift outward on stellar winds. This material accumulates around the star, forming a circumstellar envelope. It's this envelope that gives Stephenson 2-18 its infrared excess, its signature brightness in wavelengths longer than visible light. The envelope is optically thick. That means light can't pass through it without being absorbed or scattered multiple times. A photon emitted from the star's surface might scatter off 100 dust grains before finally escaping into space. By the time it does, it's lost energy. Its wavelength has shifted toward the red. The star's light is reddened by its own debris, and this tells us something about the star's state. The presence of dust means the star is cool. Hot stars don't make dust. Their radiation destroys any molecules or grains that try to form. But cool stars, stars with surface temperatures below 4,000 Kelvin, can host complex chemistry in their atmospheres. Water vapor forms. Carbon monoxide. Silicon monoxide. These molecules act as seeds for dust, grain growth. The dust also tells us the star is losing mass. Dust doesn't form in the star's atmosphere and then fall back to the surface. It forms and escapes, carried outward by radiation pressure and stellar wind. The presence of a dusty envelope is a sign of mass loss, and so the largest star in the known universe hides behind a veil of its own creation. Its light, powerful enough to outshine 440,000 suns, is filtered and reddened and dimmed until it vanishes from optical view. Only infrared telescopes can pierce the shroud and reveal what's underneath. The star isn't just large, it's hidden. And that tells us something important about the universe. The most extreme objects aren't always the most obvious. Some of the greatest phenomena are cloaked, waiting for the right tools, the right wavelengths, the right questions. But why is it so large in the first place? What process inflates a star to this absurd scale, and why doesn't it simply tear itself apart? To understand the size, you have to understand the structure. Stephenson 2-18 isn't a solid object. It's not even close. It's a layered sphere of plasma and gas, held together by gravity, powered by fusion, and suspended in a precarious balance. At the very center, the core is compact and dense, a few million kilometers across, tiny compared to the star's overall radius. The temperature exceeds 100 million Kelvin. The pressure is unimaginable. Atoms are stripped of their electrons. Nuclei slam into each other with enough force to overcome electromagnetic repulsion and fuse into heavier elements. This is where the energy comes from, not combustion. Fusion, the conversion of mass into energy, as described by Einstein's equation. Surrounding the core are shells of different elements, each undergoing its own fusion process. Hydrogen fuses into helium in one layer. Helium fuses into carbon and oxygen in another. Deeper shells are fusing neon into magnesium, oxygen into silicon, silicon into iron. The star resembles an onion, with each layer burning a different fuel. This structure is a consequence of the star's mass. When a star is born with 12 to 16 times the sun's mass, it burns hydrogen rapidly. Within a few million years, the hydrogen in the core is exhausted. The core contracts, heats up, and begins fusing helium. Meanwhile, hydrogen fusion continues in a shell around the core. As helium runs out, the process repeats. Carbon fusion begins, then neon, then oxygen. Each stage happens faster than the last because heavier elements require higher temperatures to fuse, and the star is running out of time. When the core starts fusing silicon into iron, the end is near. Iron is the turning point. Fusing elements lighter than iron releases energy. Fusing elements heavier than iron consumes energy. Once the core is filled with iron, fusion stops. The core can no longer generate outward pressure to counteract gravity. It collapses. But we'll get to that. What matters for the star's size is what happens in the outer layers. As the core contracts and heats up, the outer envelope expands. The star's total energy output increases, but the surface area increases even more. The result is that the surface cools down. The star transitions from a hot blue main sequence star to a cool red supergiant. The expansion is extreme. The outer layers are so far from the core that gravity's pull is weak. The material is barely bound to the star. Radiation pressure from the core, the momentum of photons streaming outward, can push against the outer layers, preventing them from falling inward. In some cases, the pressure is strong enough to drive material away entirely. This expansion doesn't happen overnight. It takes hundreds of thousands of years. The star swells gradually, its radius increasing by factors of hundreds or thousands. The Sun, when it becomes a red giant in about 5 billion years, will expand to roughly the orbit of Earth. Stephenson 2-18 has expanded far beyond that. Its radius extends past Jupiter, past Saturn. If you placed the star at the center of our solar system, Saturn would be orbiting inside the star's atmosphere. And the atmosphere itself is extraordinary. The density at the visible surface, the photosphere where photons finally escape into space, is less than a billionth of the Sun's surface density. It's less dense than the air at the peak of Mount Everest. Less dense than the best laboratory vacuums we've created on Earth. Yet this tenuous atmosphere is hot. 3,000 Kelvin. Hot enough to glow red. Hot enough to ionize some atoms. But cool enough for molecules to form. Cool enough for dust to condense. The temperature gradient within the star is one of the most extreme in nature. At the core, 100 million Kelvin or more. In the hydrogen-burning shell, tens of millions of Kelvin. In the helium-burning shell, millions of Kelvin. In the outer convective zone, thousands of Kelvin. The drop from core to surface spans 8 orders of magnitude in distance and 5 orders of magnitude in temperature. And the material changes as you move outward. In the core, matter exists in a state we can barely replicate in laboratories. Fully ionized plasma. Nuclei stripped bare electrons moving freely. The density is so high that nuclei are packed close together, interacting through the strong nuclear force. Fusion proceeds through quantum tunneling. Particles don't have enough energy to overcome the electromagnetic barrier classically, but they tunnel through it probabilistically. In the intermediate layers, the plasma is still ionized, but less so. Electrons begin to recombine with nuclei. The material is opaque to radiation. Photons can't travel far before being absorbed and re-emitted. Energy transport happens through radiation in some layers, through convection in others. Convection is the key to understanding the star's structure. In the outer layers, the temperature gradient is steep enough that hot material rises and cool material sinks. Convective cells form massive churning currents of plasma, each cell potentially larger than the sundae. These cells transport energy from the interior to the surface. They also dredge up material from deeper layers, bringing freshly synthesized elements to the surface. This is why the star's spectrum shows evidence of carbon, nitrogen, oxygen, and other heavy elements. These elements weren't present when the star formed. They were created by fusion in the core and brought to the surface by convection. The star's atmosphere is enriched with its own fusion products. And convection also drives instability. The cells don't move smoothly. They turbulently churn and collide. They create pressure waves that propagate through the star. Sometimes these waves reach the surface and cause the star to pulsate. The radius expands and contracts. The luminosity varies. The mass loss rate spikes. Red supergiants are inherently unstable. Their structure is too extended. The connection between core and surface is too tenuous. The balance between radiation pressure and gravity is too delicate. Small perturbations can trigger large responses. This is why the density is so low. The mass is concentrated in the core and the inner shells. The outer envelope, which makes up most of the star's volume, is thin and diffuse. If you were to compress Stephenson 2-18 into a sphere with the sun's density, it would shrink to a fraction of its current size. But you can't. The physics doesn't allow it. The star is what it is because of the interplay between core fusion, gravitational collapse, and radiation pressure. The gradient from core to surface is staggering. Temperature drops from 100 million Kelvin to 3000 Kelvin. Density drops from billions of grams per cubic centimeter to less than a billionth of a gram per cubic centimeter. Pressure drops from values we can barely compute to near vacuum. All of this happens within a radius of 1.5 billion kilometers, and the material itself changes state as you move outward. Deep in the core, you have fully ionized plasma atomic nuclei and free electrons moving at relativistic speeds. In the intermediate layers, electrons begin to recombine with nuclei, forming partially ionized plasma. In the outer envelope, atoms are mostly neutral. Molecules begin to form: water vapor, carbon monoxide, silicate dust. The star's outer atmosphere is cool enough for chemistry. The boundary between layers isn't sharp. There's no hard division where one layer ends and another begins. The transition is gradual. The properties change smoothly though, sometimes rapidly, but the overall picture is clear. The star is stratified. Each layer has its own composition, its own temperature, its own density, its own physics, and all of it is held together by gravity. The core's gravity pulls on the shells. The shells pull on the envelope. The envelope is barely held. If the star were any larger, the outer layers would escape entirely. If it were any smaller, it wouldn't be a red supergiant. The star exists in a narrow range of parameter space. Too massive, and it would blow itself apart through radiation pressure. Too small, and it wouldn't have enough mass to fuse heavy elements. Too young, and the core wouldn't have evolved to the point where the envelope expands. Too old, and the star would have already exploded. Stephenson 2-18 occupies a precise moment in stellar evolution. A fleeting phase where the structure is maximally extended, where the radius is as large as physics permits, where the balance between forces is so delicate that the slightest change could tip it over the edge. This is the paradox of red supergiants. They're the largest stars, but also the least dense. They're the brightest but also the coldest on the surface. They're the most massive but also the most unstable. Everything about them is a study in extremes. And Stephenson 2-18 sits at the upper edge of what's possible. If it were significantly larger, radiation pressure would blow the outer layers into space. If it were significantly smaller, it wouldn't be a red supergiant, it would be something else entirely. The star exists in a narrow band of parameter space, a fleeting state in the life cycle of massive stars. The structure is fragile, the balance is temporary, and the star is already starting to lose it. Which brings us to the question, how long does a star like this actually last? The Sun has been burning for 4.6 billion years. It has another 5 billion years to go. Stephenson 2-18. Maybe 30 million years total. Possibly less. That's not a typo. 30 million years. The Sun will outlive it by a factor of more than 300. Stephenson 2-18 is massive, luminous, and spectacular, and it's also racing toward its death at a speed that defies intuition. The relationship between mass and lifespan is inverse. Small stars live long. Red dwarfs with a tenth of the Sun's mass can burn for trillions of years. The Sun at 1 solar mass gets 10 billion. A star with 10 times the Sun's mass, maybe 20 million years. Stephenson 2-18 with 12 to 16 times the Sun's mass, 30 to 50 million years, and it's already well into that span. The reason is fuel consumption. Massive stars have more hydrogen to burn, yes, but they burn it far faster. Gravity pulls inward with enormous force. To counteract that force, the core must generate enormous pressure, and pressure comes from fusion. The more mass you have, the harder gravity pulls, the hotter the core has to be, the faster fusion proceeds. It's a runaway process. More mass means more gravity. More gravity means higher core temperature. Higher core temperature means faster fusion. Faster fusion means more energy output. More energy output means higher luminosity. Stephenson 2-18 shines 440,000 times brighter than the Sun because it's burning through its fuel at a furious rate. And it's not just burning hydrogen anymore. The core has moved through multiple fusion stages. Hydrogen to helium, helium to carbon and oxygen, carbon to neon, neon to magnesium, oxygen to silicon, silicon to iron. Each stage releases less energy than the last. Each stage proceeds faster than the last. Hydrogen fusion, the first stage, lasts for millions of years. Helium fusion, maybe 1 million years. Carbon fusion, tens of thousands of years. Neon fusion, a few years. Oxygen fusion, months. Silicon fusion, days. When the core is fusing silicon into iron, the star has days left. Not days until it dims or cools. Days until it dies. But Stephenson 2-18 isn't fusing silicon yet. It's still in an earlier stage, likely oxygen or neon fusion. That gives it a bit more time, but not much. The clock is ticking. The speed at which massive stars age is almost incomprehensible. Imagine compressing a human lifetime into a single day. You're born at sunrise. By noon, you're middle-aged. By sunset, you're elderly. By midnight, you're gone. That's what stellar evolution looks like for a star like Stephenson 2-18, except the day is 30 million years instead of 24 hours. And the star doesn't age gracefully. Each fusion stage is more violent than the last. Hydrogen fusion is relatively stable. The proton-proton chain proceeds smoothly, releasing energy at a steady rate. But by the time you reach carbon fusion, the process is turbulent. Temperature spikes trigger runaway reactions. The core contracts and heats up between stages. Convection intensifies. The star becomes increasingly unstable. The instability manifests in pulsations. The star's radius varies. Not by small amounts, by significant fractions of its total size. The outer layers expand and contract in irregular cycles. Sometimes the pulsations are driven by opacity changes in the atmosphere. Sometimes they're driven by pressure waves from the core. Either way, the star is no longer in steady equilibrium. These pulsations affect the mass loss rate. When the radius expands, the surface gravity drops. Material that was barely bound becomes unbound. The stellar wind intensifies. More mass is shed. When the radius contracts, the wind weakens. But the average mass loss rate increases over time as the pulsations become more violent. And while the core is racing through fusion stages, the outer envelope is doing something equally dramatic. It's bleeding mass into space. Every 3 years, the star loses the equivalent of 1 Earth's worth of material. That's 1 Earth mass, roughly 6 times 10 to the 24th kilograms expelled into the interstellar medium every 3 years. For comparison, the Sun loses about 1 Earth mass every 150 million years. Stephenson 2-18 is losing mass 50 million times faster. This mass loss is driven by stellar wind. Not the gentle breeze of particles that streams from the Sun, but a torrential outflow of gas and plasma. The wind speed is around 10 kilometers per second, slow by stellar wind standards, but the sheer volume of material makes up for the lack of speed. Billions of tons per second are flowing outward, carried by radiation pressure and thermal energy. The mass loss rate is approximately 1.35 times 10 to the -5 solar masses per year. That sounds abstract. Translation: in a million years, the star will lose about 13 solar masses. But the star only has 12 to 16 solar masses total. It can't sustain this rate for much longer, and the rate isn't constant. Red supergiants pulsate. Their outer layers expand and contract in irregular cycles. Sometimes the pulsations are driven by internal waves propagating through the star. Sometimes they're triggered by convection, massive cells of hot plasma rising and cool plasma sinking, churning the atmosphere like a pot of boiling water. Each cell can be larger than the sundae. When they reach the surface, they disrupt the equilibrium and eject shells of material. These pulsations can temporarily increase the mass loss rate. During an outburst, the star might shed several Earth masses in a single event. The material forms a shell that expands outward, cools, and eventually merges with the circumstellar envelope. And the envelope itself is enormous. It extends for light years around the star. The material inside it, hydrogen, helium, carbon, oxygen, silicon, iron, and trace amounts of dozens of other elements, represents everything the star has synthesized and expelled over its lifetime. It's a record of the star's chemical evolution, written in gas and dust. But the envelope also tells us something else. It tells us the star is dying. Mass loss is a symptom of instability. Stable stars don't eject significant amounts of material. The Sun's solar wind is negligible compared to its total mass. The Sun will lose less than 1% of its mass over its entire lifetime. But red supergiants are not stable. They're in the final throes of their lives, struggling to maintain equilibrium between the crushing force of gravity and the explosive force of fusion. And the mass loss has consequences. Every bit of material that escapes takes energy with it. The star's gravitational binding energy decreases. The star becomes less tightly bound, more vulnerable to disruption. At the same time, the mass loss removes the outer layers that would otherwise participate in the supernova explosion. If the star loses enough mass, the envelope might be completely stripped away before the core collapses. The result would be a different kind of stellar death, not a supernova, but something subtler. The exposed core, hot and dense, would continue fusing until it exhausted its fuel, then collapse into a neutron star or black hole without the spectacular fireworks. But for most massive stars, the mass loss isn't fast enough to prevent a supernova. The outer layers are still there when the core collapses, and Stephenson 2-18, with its enormous size and relatively low mass loss rate compared to some other red supergiants, will almost certainly go supernova. And soon, cosmically speaking, that struggle will end. The timeline is uncertain. The star could explode tomorrow. It could explode in 100,000 years. We don't have precise enough measurements to predict the exact moment, but we know it's close. The star is in the final stages of its life. The core is fusing heavy elements. The envelope is pulsating and shedding mass. The balance is precarious. And when the balance finally tips, the consequences will be extraordinary. So you have a star that's enormous, luminous, and fragile. A star that's burning through its fuel at a rate that would exhaust our sun in a geological eye blink. A star that's shedding mass like a leaking balloon surrounded by a shell of its own debris. What happens when the fuel runs out? Stephenson 2-18 is shedding mass at a furious rate. Every 3 years, it loses the equivalent of 1 Earth's worth of material. Not gradually, continuously. A stream of gas and plasma flowing outward, driven by stellar wind. Stellar wind isn't like wind on Earth. It's not air moving because of temperature differences. It's matter being expelled from the star's surface because radiation pressure and thermal energy overcome gravity's hold. For the Sun, the solar wind is a gentle breeze about 1 million tons per second. For Stephenson 2-18, it's a deluge, thousands of times stronger. The wind carries atoms, molecules, ions, and electrons. Hydrogen and helium dominate, but heavier elements are mixed in carbon, nitrogen, oxygen, silicon, iron. These elements were forged in the star's core and dredged up to the surface by convection. They're being returned to the interstellar medium where they'll eventually contribute to the formation of new stars, planets, and perhaps life. The speed of the wind is relatively slow, around 10 kilometers per second. That's slow compared to the stellar winds from hot blue stars, which can exceed 1,000 kilometers per second. But the sheer volume of material makes up for the lack of speed. The mass loss rate is roughly 1.35 times 10 to the negative 5 solar masses per year. That's a technical way of saying an enormous amount. As the wind flows outward, it cools. Atoms bond into molecules. Molecules condense into grains. Dust forms. This is how the circumstellar envelope builds up around the star. The envelope extends for light years in every direction, a vast cocoon of gas and particles. It's this envelope that blocks visible light and creates the infrared signature we detect from Earth. The dust formation process is remarkable. In the star's atmosphere, temperatures are around 3000 Kelvin, hot enough to keep most atoms ionized or in gaseous form. But as the material moves outward in the stellar wind, it expands and cools. By the time it reaches a few stellar radii out, the temperature has dropped to below 1000 Kelvin, cool enough for chemistry. Silicon and oxygen combine to form silicon monoxide, then silicon dioxide. These molecules collide and stick together, building up larger structures. Eventually, they form microscopic grains of silicate, the same material that makes up sand on Earth, but formed in the atmosphere of a dying star. Carbon follows a similar path. Carbon atoms bond into chains, then rings, then complex three-dimensional structures. Eventually, they form soot-like particles. Amorphous carbon dust. These grains are tiny, 1/10 of a micrometer across, about the wavelength of blue light. And that's why they're so effective at blocking it. When blue light hits a dust grain, it scatters in random directions. Most of it never makes it through. Red light, with its longer wavelength, scatters less efficiently. Some of it gets through. Infrared light, with even longer wavelengths, passes through with minimal absorption. The result is that the star's spectrum is heavily modified by its own dust. The blue and green light are almost completely absorbed. The red light is partially absorbed. The infrared light shines through. This is why Stephenson 2-18 appears as a bright infrared source, but is invisible in optical wavelengths. The envelope also emits radiation. Maser emission, specifically microwave amplification by stimulated emission of radiation. Water molecules in the envelope are excited by the star's radiation and emit coherent microwave signals. These signals are detectable with radio telescopes and serve as a diagnostic tool. They tell us about the temperature, density, and velocity structure of the material around the star. Maser emission requires specific conditions. The molecules need to be excited to a particular energy state. They need to be in an environment where stimulated emission can occur, and they need a source of pumping energy, in this case, the star's infrared radiation. The fact that we detect water maser emission from Stephenson 2-18 tells us that water molecules exist in the circumstellar envelope. That might seem surprising. Water in the atmosphere of a star, but at a few stellar radii, out where the temperature has dropped to a few hundred Kelvin, water is stable. And under the right conditions, it emits maser radiation. The presence of water also tells us about the chemistry of the envelope. Oxygen is abundant. It's one of the primary fusion products in the star's core. Hydrogen is everywhere. Put them together in a cool environment and you get water. You also get hydroxyl radicals, carbon monoxide, silicon monoxide, and a host of other molecules. The circumstellar envelope is a chemistry lab, a place where atoms synthesized in stellar fusion combine into molecules which then condense into dust. It's a factory for the building blocks of planets. But the mass loss isn't uniform. Red supergiants are unstable. Their outer layers pulsate. Sometimes the pulsations are regular, driven by the star's internal structure. Sometimes they're chaotic, triggered by convection cells the size of planets churning through the atmosphere. These pulsations can temporarily increase the mass loss rate, ejecting shells of material in discrete events. When a pulsation reaches the surface, it creates a shock wave. The shock wave compresses the atmosphere, heats it, and accelerates it outward. Material that was moving at 10 kilometers per second suddenly jumps to 20 or 30 kilometers per second. The mass loss rate spikes. A shell of material is ejected. These shells are visible in some red supergiants. Not as optical structures, the dust blocks that, but as infrared shells. Rings of warm dust expanding outward from the star. Each ring represents a discrete ejection event, a moment when the star pulsated and threw off a shell of material. Over time, these shells merge. They collide with previously ejected material. They form a complex layered structure around the star. The circumstellar envelope isn't smooth. It's clumpy with regions of higher and lower density, hotter and cooler temperatures. The star isn't creating this wind consciously. It's not deciding to shed mass. The process is mechanical, dictated by physics. Radiation from the core pushes outward. Gravity pulls inward. When radiation wins, even temporarily, material escapes. The star has no choice in the matter. And the wind doesn't just carry gas, it carries energy. Kinetic energy as the particles move outward. Thermal energy as the gas cools. Radiative energy as atoms and molecules emit photons. All of this energy originated in the core, where fusion converts mass into energy. The wind is a delivery mechanism, transporting that energy from the star into the surrounding space. The material expelled by the wind doesn't vanish. It accumulates in the circumstellar envelope, which grows denser and more opaque over time. Eventually, the envelope becomes so thick that it blocks most of the star's optical light. The star becomes invisible in visible wavelengths, but blazes in infrared. This is the state Stephenson 2-18 is in, and the dust in the envelope serves another purpose. It's the seed material for future planetary systems. The silicate grains, the carbon, soot, the metallic particles, these are the building blocks of planets and asteroids. When the star dies and the envelope disperses, this material will mix with the interstellar medium. Millions or billions of years later, it might collapse under gravity to form a new star with new planets. Every atom in your body passed through a stellar wind like this at some point. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was synthesized in the core of a massive star expelled in a stellar wind, incorporated into a cloud of gas and dust, and eventually assembled into the Earth. You are made of stardust, not metaphorically, literally. The atoms in your body are older than the Sunday. They've been through multiple generations of stars. They've been forged in fusion, scattered in winds, collected in clouds, condensed into planets. And Stephenson 2-18 is contributing to that cycle. Its wind is seeding the galaxy with heavy elements. When it dies, and it will die soon, it will contribute even more. But the wind is just the prelude. The real event is still to come. At some point, it could be tomorrow. It could be 100,000 years from now. The core of Stephenson 2-18 will run out of fuel. The last fusion reaction will complete. The last photon will escape the core, and gravity will win. The collapse will be sudden. The core, which has been held up by the pressure of fusion, will lose its support. Electrons, protons, and neutrons will be crushed together. The core will shrink from something the size of Earth to something the size of a city in less than a second. The physics of core collapse is extreme. The core's density rises to values that dwarf anything we encounter in everyday life. Atoms are compressed so tightly that electrons are forced into atomic nuclei. Protons and electrons combine to form neutrons. The core becomes a sea of neutrons packed so densely that a teaspoon would weigh 1 billion tons. This is called neutronization. It's a process that can only occur under extreme pressure. Under normal conditions, a free neutron is unstable. It decays into a proton, an electron, and an antineutrino in about 10 minutes. But when you compress matter to densities exceeding 1 billion tons per cubic centimeter, the reverse process becomes favorable. Protons capture electrons and turn into neutrons. And neutronization releases neutrinos, vast quantities of them. Neutrinos are ghostly particles that barely interact with matter. They can pass through light years of lead without being absorbed. When the core collapses, it releases roughly 10 to the 58 neutrinos in a few seconds. That's more neutrinos than all the stars in the observable universe emit in a year. The collapse releases an enormous amount of gravitational energy, roughly 10 to the 46 joules. That's a 1 followed by 46 zeros. It's equivalent to the energy the sun will radiate over its entire 10 billion year lifetime, but compressed into a few seconds. Most of that energy goes into neutrinos, which stream outward and escape into space. But a small fraction, maybe 1%, goes into kinetic energy. It drives a shockwave outward through the star's outer layers. The shockwave is a wall of compressed superheated gas traveling at tens of thousands of kilometers per second. It rips through the onion shell structure of the star, heating each layer to billions of degrees. The sudden heating triggers explosive fusion. Elements heavier than iron elements that can't be formed in normal stellar fusion are synthesized in seconds. This is where gold comes from. Platinum, uranium, all of the elements heavier than iron. They can't be made in the core of a star because fusing them consumes energy rather than releasing it. But in the extreme conditions of a supernova shockwave, there's energy to spare. Nuclear reactions that would never occur under normal conditions proceed rapidly. The R process, rapid neutron capture, is the primary mechanism. Atomic nuclei are bombarded with neutrons. They capture one, then another, building up heavier and heavier elements in a matter of seconds. The process is so fast that unstable isotopes don't have time to decay before capturing more neutrons. The result is a full suite of heavy elements. Every element in the periodic table heavier than iron. Every atom of gold in a wedding ring. Every atom of platinum in a catalytic converter. Every atom of uranium in a nuclear reactor. All of them forged in the final seconds of a dying star. The shock wave reaches the surface and blows the star apart. The outer layers, everything outside the core, are ejected into space at a significant fraction of the speed of light. The explosion is called a supernova. Type 2 specifically because it's triggered by core collapse rather than accretion. For a few weeks, the supernova will outshine the entire galaxy. Hundreds of billions of stars, and this one dying star will be brighter than all of them combined. From Earth 19,000 light-years away, it will be visible to the naked eye. Not as bright as the full moon, but brighter than any star in the sky. Bright enough to cast shadows at night. The peak brightness occurs when the expanding debris cloud becomes optically thin. Initially, the ejected material is opaque. Photons can't escape. They're trapped inside, heating the debris. But as the debris expands, its density drops. Eventually, it becomes transparent. The trapped photons escape all at once. The supernova brightens dramatically. The brightness is powered by radioactive decay. Nickel-56 synthesized in the explosion decays into cobalt-56 with a half-life of 6 days. Cobalt-56 decays into iron-56 with a half-life of 77 days. Each decay releases gamma rays. The gamma rays heat the expanding debris. The debris re-radiates the energy as visible light. This is why supernovae have characteristic light curves. They brighten rapidly, peak within a week or two, then fade over months. The fade rate is determined by the radioactive decay rates. Measure the light curve, and you can infer the amount of nickel-56 produced in the explosion. The last time a supernova was visible to the naked eye from Earth was in 1987. Supernova 1987A in the Large Magellanic Cloud. That star was 168,000 light-years away. Stephenson 2-18 is closer, much closer. Its supernova will be spectacular. The explosion will be bright enough to read by at night. It will be visible during the day, a point of light in the sky, competing with the Sunday. It will dominate the constellation Scutum for weeks, then gradually fade over months and years. And the debris will keep expanding. The shockwave will sweep through the interstellar medium, creating a supernova remnant, a glowing shell of gas and dust expanding at thousands of kilometers per second. The Crab Nebula is a supernova remnant from a supernova that occurred in 1054. Nearly 1,000 years later, it's still visible, still expanding. Stephenson 2-18's remnant will be visible for thousands of years. Long after the initial flash has faded, the remnant will remain a testament to the star that was. But the fireworks are only part of the story. The supernova will also create something new. The core, crushed to unimaginable density, doesn't bounce back. It stays compressed. If the core mass is below a certain threshold, about 2 to 3 times the Sun's mass, it stabilizes as a neutron star. A sphere 20 kilometers across, composed entirely of neutrons packed so tightly that a teaspoon would weigh 1 billion tons. Neutron stars are the densest objects in the universe aside from black holes. They're so dense that a sugar cube of neutron star material would weigh as much as all of humanity combined. The gravitational field at the surface is about 200 billion times stronger than Earth's. If you tried to stand on a neutron star, and you can't because you'd be vaporized instantly, you'd be flattened into a layer a few atoms thick. Neutron stars spin fast. Some rotate hundreds of times per second. They emit beams of radiation from their magnetic poles like cosmic lighthouses. If the beam sweeps across Earth, we detect a pulse. These objects are called pulsars. The fastest known pulsar spins 716 times per second. Its equator is moving at roughly 20% of the speed of light. The centrifugal force is enormous, but not enough to tear the star apart. Neutron degeneracy pressure holds it together, but if the core mass exceeds the threshold, if it's more than about 3 solar masses, neutron degeneracy pressure can't hold it up. The core continues to collapse. It shrinks past the point where escape velocity equals the speed of light. It becomes a black hole. Black holes don't emit light. They don't have a surface. They're not objects in the traditional sense. They're regions of space-time so warped that nothing, not even light, can escape once it crosses the event horizon. The event horizon is the boundary. Inside, all paths lead inward. Outside, escape is still possible. For a black hole formed from the core of Stephenson 2-18, the event horizon would be roughly 60 to 90 kilometers across. Tiny compared to the star itself, but permanent, indestructible. The black hole will outlast everything. Stars will burn out. Galaxies will fade. The universe will expand into darkness. And the black hole will still be there, slowly evaporating through Hawking radiation over timescales that dwarf the current age of the universe. Which fate awaits Stephenson 2-18, neutron star or black hole? It depends on the core mass, which depends on how much mass the star has lost in its lifetime. If the mass loss rate has been high, and it has, the core might be light enough to form a neutron star. If not, it'll collapse into a black hole. We won't know until it happens. But either way, the star will die. And when it does, it will contribute to the galaxy in ways that are hard to overstate. So, what's keeping Stephenson 2-18 from exploding right now? What's the delay? The answer is fuel. As long as the core has something to fuse, it can generate pressure. And as long as it can generate pressure, it can resist gravity. The star is in a race between fusion and collapse. Fusion is losing, but it hasn't lost yet. The core is fusing heavier and heavier elements. Each stage buys the star a little more time, but each stage also produces less energy. Hydrogen fusion converts about 0.7% of the mass into energy. Helium fusion, about 0.1%. Carbon fusion, even less. By the time you get to silicon fusion, the energy yield is minimal. And there's a hard stop: iron. When the core tries to fuse iron, it doesn't release energy. It absorbs it. Fusion beyond iron is endothermic. It takes more energy than it gives back. The core can't sustain itself by fusing iron. When the core becomes iron, fusion stops. And without fusion, there's no pressure. Without pressure, there's no resistance to gravity. The core collapses. But Stephenson 2-18 hasn't reached that point yet. The core is still working through the earlier stages. Oxygen, maybe neon. It still has time. Maybe a few thousand years. Maybe a few 100,000. On human timescales, that's a long time. On cosmic timescales, it's nothing. The progression through fusion stages follows a predictable pattern. Each element requires a higher temperature to fuse than the previous one. Hydrogen fuses at around 10 million Kelvin. Helium requires 100 million. Carbon needs 600 million. Neon 1.2 billion. Oxygen 1.5 billion. Silicon 2.7 billion. As the core exhausts one fuel, it contracts. The contraction releases gravitational energy, which heats the core. The temperature rises until it's hot enough to fuse the next element. Then a new fusion stage begins. The process repeats over and over each time, with a heavier element and a higher temperature. But there's a cost. Each contraction makes the core denser. Each new fusion stage proceeds faster than the last. The star is accelerating toward its end, and the outer layers know nothing about this. The photons generated in the core take thousands of years to diffuse outward through the star. By the time they reach the surface, they've been absorbed and re-emitted countless times. The surface of the star reflects the state of the core from thousands of years ago, not its current state. This means the star could already be on the verge of collapse, and we wouldn't know. The light we see today was generated by fusion reactions that occurred millennia ago. The core could be fusing silicon right now. It could have days left, and we wouldn't see any change in the star's appearance until thousands of years after the collapse occurred. The disconnect between core and surface is one of the strange features of stellar structure. Information travels slowly in stars, not because light is slow, but because the material is opaque. Photons can't travel far before being absorbed. They random walk through the star, taking thousands or millions of years to escape, and the star knows it's dying. Not consciously, but the physics knows. The mass loss rate is a symptom. The star is shedding its outer layers because it can't hold them anymore. Radiation pressure is winning against gravity. The star is coming apart slowly, layer by layer. If the mass loss continues, the star might shed so much material that it never reaches the supernova stage. It might lose the outer envelope entirely, leaving behind a hot, dense core, a Wolf-Rayet star, or something similar. These objects are rare. They're the exposed cores of massive stars that have blown away their outer layers. Wolf-Rayet stars are among the hottest stars known. Surface temperatures exceeding 50,000 Kelvin. They're small, only a few solar radii, but incredibly luminous. They emit powerful stellar winds, even stronger than red supergiant winds. And they're chemically peculiar. Their spectra show emission lines from highly ionized elements, carbon, nitrogen, oxygen elements that should be buried in the core but are now visible at the surface because the outer layers have been stripped away. Some astronomers think Stephenson 2-18 might transition to a Wolf-Rayet phase before exploding. The mass loss rate is high enough that the hydrogen envelope could be completely removed within a few 100,000 years. What would be left is the helium core exposed, and hot burning helium and heavier elements. But for most massive stars, the mass loss isn't fast enough to prevent a supernova. The outer layers are still there when the core collapses. And Stephenson 2-18, with its enormous size and relatively low mass loss rate compared to some other red supergiants, will almost certainly go supernova. The uncertainty is frustrating. We can model stellar evolution. We can predict the general sequence of events, but we can't predict the exact timing. The moment of collapse depends on details we can't observe. The exact composition of the core, the exact temperature and pressure distribution, the exact mass loss history. Small changes in initial conditions can lead to large changes in outcomes. A star with 12 solar masses might live 30 million years. A star with 16 solar masses might live 20 million. The difference is 6 million years. Enormous on human timescales, negligible on cosmic timescales. And Stephenson 2-18's mass is uncertain. We estimate 12 to 16 solar masses based on models and observations. But the true value could be anywhere in that range. And that uncertainty translates to uncertainty in the remaining lifetime. The star could explode tomorrow. Literally, tomorrow. The core could collapse tonight, and we'd see the supernova in 19,000 years. Or it could happen 19,000 years from now and our descendants would see it in 38,000 years. We don't know. But we do know this: the star is in the final phase of its life. The core is fusing heavy elements. The envelope is unstable. The balance is precarious. The end is near, and when it does, we'll see it. From 19,000 light-years away, we'll see a new star appear in the constellation Scutum. It'll brighten over the course of days, reaching its peak in a few weeks. It'll stay bright for months, maybe years. Then it'll fade slowly until it's gone. But the light we see won't be from the explosion itself. It'll be from the radioactive decay of isotopes created in the explosion. Nickel-56 decaying into cobalt-56, then into iron-56. Each decay releases gamma rays, which heat the expanding debris, which re-radiates the energy as visible light. The supernova will glow like a cosmic ember powered by nuclear decay. And the debris will keep expanding. The shock wave will sweep through the interstellar medium, creating a supernova remnant, a glowing shell of gas and dust, expanding at thousands of kilometers per second. The Crab Nebula is a supernova remnant from a supernova that occurred in 1054. Nearly 1,000 years later, it's still visible, still expanding. Stephenson 2-18's remnant will be visible for thousands of years. Long after the initial flash has faded, the remnant will remain a testament to the star that was. But it's also worth considering, what if it already happened? The star is 19,000 light-years away. The light we see left the star 19,000 years ago. If the star exploded 10,000 years ago, we won't know for another 9,000 years. The explosion could have happened during the last ice age and we wouldn't see it until the year 11,000 or so. Or it could happen tomorrow, or 1,000,000 years from now. We don't know. We can't know. All we can do is watch and wait and prepare. But in a sense, the timing doesn't matter. The star's fate is sealed. It will die. It will explode. It will leave behind a neutron star or a black hole. It will enrich the galaxy with heavy elements. It will trigger the formation of new stars. The supernova will inject energy into the interstellar medium. The shock wave will compress nearby gas clouds, triggering star formation. The heavy elements synthesized in the explosion will enrich the chemical composition of the galaxy, making it possible for planets like Earth to form, for life like us to exist. Every atom of gold in the wedding ring, every atom of iodine in the thyroid gland, every atom of uranium in a nuclear reactor, all of them were forged in the death of a star, like Stephenson 2-18. You are not just made of stardust. You are made of supernova debris. And somewhere out there, 19,000 light-years away, the largest star we've ever found is preparing to become the next chapter in that story. And someday, billions of years from now, some of the atoms expelled by Stephenson 2-18 might find their way into a new planet orbiting a new star. And maybe, just maybe, those atoms will become part of a living thing. They live, they die, they return their material to the cosmos, and the cycle repeats. Stephenson 2-18 is part of that cycle, a brief, brilliant flash in the story of the universe. But there's one more thing to consider, a deeper question. Why does the star exist at all? Physics imposes limits. The speed of light is a limit. The temperature of absolute zero is a limit. And stellar size is a limit. There's a maximum size a star can reach before it becomes unstable and tears itself apart. That limit is called the Eddington limit, named after Arthur Eddington, who derived it in the early 20th century. The Eddington limit is the point where radiation pressure equals gravitational force. Radiation pressure is the outward push of photons streaming from the core. Gravitational force is the inward pull of the star's mass. When the two are equal, the star is in equilibrium. If radiation pressure exceeds gravity, the star blows itself apart. If gravity exceeds radiation pressure, the star collapses. For most stars, radiation pressure is much weaker than gravity. The sun's radiation pressure is negligible. Gravity dominates. But for massive luminous stars, radiation pressure becomes significant. And for the most massive stars, it approaches the Eddington limit. Stephenson 2-18 is close to that limit. Its luminosity is 440,000 times the sun's. Its mass is only 12 to 16 times the Sun's. That's a very high luminosity to mass ratio. The radiation pressure is enormous. If the star were more luminous or less massive, it would exceed the Eddington limit. Radiation would overcome gravity. The outer layers would be blown away. The star would disintegrate. But it hasn't. The star exists, which means it's just below the limit. It's as large as physics allows, but not larger. And that raises a question. Why don't we see stars that are larger? Why isn't there a star with a radius of 5,000 solar radii, or 10,000? The answer is instability. Stars larger than a certain size can't maintain equilibrium. They pulsate violently. They eject mass. They lose their outer layers. They shrink. Theoretical models suggest that the maximum radius for a red supergiant is around 1,500 to 2,000 solar radii. Stephenson 2-18 at 2,150 solar radii is slightly above that limit, which means either the measurements are wrong possible given the uncertainties, or the star is in an unusually unstable state. If the latter, the star might be shedding mass even faster than we think. It might be in the process of shrinking. Or it might be caught in a transient phase, a brief moment where the radius exceeds the theoretical maximum before the star adjusts. Either way, the star is pushing the boundaries of what's physically possible, and that's true for mass as well. There's an upper limit on stellar mass set by a different mechanism. When a star forms, it accretes matter from a surrounding cloud, but as the star grows more massive, its radiation pressure increases. Eventually, the radiation is strong enough to blow away the infalling material. The star can't accrete any more mass. It stops growing. The upper mass limit is somewhere around 150 to 200 solar masses at birth. Stars more massive than that can't form, or they lose mass so quickly that they shrink below the limit. But Stephenson 2-18 was born with 12 to 16 solar masses. It's not a particularly massive star by those standards, and yet it's the largest. The size comes from evolution. As the star ages, the core contracts and the envelope expands. The star becomes a red supergiant. The radius increases by a factor of hundreds or thousands. But the mass doesn't change much aside from what's lost in the stellar wind. So the star is large because it's old. Not old in years, only 30 to 50 million, but old in terms of its life cycle. It's near the end, and red supergiants are always near the end. Stars don't spend much time as red supergiants. The phase lasts a few 100,000 years, maybe a few million. That's a tiny fraction of the star's total lifespan. Most of the time, the star is either a main sequence star, hot blue compact, or it's dead. We're seeing Stephenson 2-18 during a brief window, a moment in cosmic history when this star happens to be inflated to its maximum size. In another million years, it'll be gone, replaced by a neutron star or a black hole surrounded by an expanding cloud of debris, and we're lucky to see it. Red supergiants are rare. There are only a few hundred known in the entire Milky Way. Most stars never become red supergiants. They're not massive enough. They end their lives as white dwarfs, not supernovae. But the stars that do become red supergiants are spectacular. They're the giants of the stellar world. They're the stars that push physics to its limits. They're the stars that create the heavy elements we depend on. And they're the stars that remind us how strange the universe is. A star so large it would engulf half the solar system, yet so diffuse you could pass through it. A star so luminous it outshines hundreds of thousands of suns, yet so obscured we can't see it with our eyes. A star so massive it will die in a cosmic fireball, yet so fragile it's already falling apart. Stephenson 2-18 is a paradox, an impossibility that exists anyway, a structure that shouldn't hold together but does for just a little while longer, and somewhere 19,000 light-years away it's still shining, still burning, still shedding its outer layers into the void. It doesn't know we're watching. It doesn't care. It's a star. It follows the laws of physics. It has no awareness, no purpose, no intent, but it exists. And that existence is remarkable. Consider what it takes to make a star like this. You need a cloud of gas hundreds of light years across. You need gravity to collapse it. You need the collapse to form a dense core. You need the core to heat up until fusion ignites. You need the star to burn for millions of years, fusing hydrogen into helium, helium into carbon, carbon into oxygen. You need the core to contract and the envelope to expand. You need the star to reach this precise moment in its evolution, where it's as large as physics allows. And then you need someone somewhere to look up and notice. We are that someone. We built the telescopes. We developed the theory. We measured the distance, calculated the radius, estimated the mass. We pieced together the story of this star from photons that traveled 19,000 years to reach us. And the story is, this Stephenson 2-18 is a giant among giants, a star at the edge of possibility, a cosmic furnace in its final days, shining across the void, waiting for the moment when fusion stops and gravity wins. It will happen. Soon on cosmic timescales, the core will collapse. The supernova will erupt. The light will reach Earth. And for a few weeks, we'll have a new star in the sky brighter than anything else. And then it'll fade. And the star that was Stephenson 2-18 will be gone, leaving behind only a remnant. A neutron star or a black hole, a shell of expanding debris, and the memory of the largest star we've ever seen. But the atoms will remain, the iron, the carbon, the oxygen, the silicon, all of it scattered into space, mixed with the interstellar medium, waiting to become part of something new, waiting to become part of the next generation of stars, the next generation of planets, the next generation of life. The cycle continues. Stars die so that new stars can be born. Supernovae enrich the galaxy so that planets can form, so that life can arise, so that creatures like us can exist and look up and wonder. We are the universe contemplating itself, made of atoms forged in stars like Stephenson 2-18, born from the debris of dead stars, alive for a brief moment in cosmic history, aware, conscious, capable of understanding. And that understanding tells us something profound. The universe is not static, it's evolving. Stars are born, stars die, elements are created, structures emerge, complexity increases, and somewhere in that process, matter became alive, became aware, became capable of building telescopes and detecting infrared radiation and calculating the radius of a star 19,000 light years away. That's the real story of Stephenson 2-18. Not just that it's large, not just that it's dying, but that we can know it, that we can measure it, that we can tell its story. The star doesn't care, but we do, and that makes all the difference.